Lesson: Odd and even functions. You must learn to deal with the odd and even in life, as well as in figures. George Eliot. Definition of even functions. A function f is even if, for every x in the domain, the number negative x is also in the domain, and f of negative x equals f of x. Let's look at the graph of the quadratic function f of x equals x squared minus 1. A, negative 1, 0 belongs to the graph of function f. B, 1, 0 also belongs to the graph of function f. F of negative 1 equals 0. F of 1 equals 0. Thus, f of negative 1 equals f of 1. The negative sign in the argument of the function is absorbed. It disappears. The points A and B are symmetric with respect to the y-axis. F negative 2, 3 belongs to the graph of function f. E 2, 3 also belongs to the graph of function f. F of negative 2 equals 3. F of 2 equals 3. Thus, f of negative 2 equals f of 2. The negative sign in the argument of the function is absorbed. It disappears. The points f and e are symmetric with respect to the y-axis. P x f of x belongs to the graph of function f. R negative x f of negative x also belongs to the graph of function f. F of negative x equals f of x. The negative sign in the argument of the function is absorbed. It disappears. The points R and P are symmetric with respect to the y-axis. A function f is even if and only if, whenever xy is on the graph of f, then the point negative xy is also on the graph. Theorem: a function is even if and only if its graph is symmetric with respect to the y-axis. Determine which of the functions below are even. A. Yes, a is an even function. This is because the graph of function a is symmetric with respect to the y-axis, as can be seen graphically. B is also an even function, because it is symmetric with respect to the y-axis. F of x is equal to f of negative x. Now in the case of C, we can clearly see that there is no symmetry with respect to the y-axis, and that, therefore, the function is not even. D is another example of a function that is not even, because it clearly shows a lack of symmetry with respect to the y-axis. Definition of odd functions. A function f is odd if for every x in the domain, the number negative x is also in the domain, and f of negative x equals negative f of x. Let's look at the graph of the cubic function f of x equals 0.05 x cubed minus 1.25x. D, negative 3, 2.4, belongs to the graph of function f. E3, negative 2.4, also belongs to the graph of function f. F of negative 3 is equal to 2.4. F of 3 is equal to negative 2.4. Thus, f of negative 3 is equal to negative f of 3. The negative sign in the argument of the function moves in front of the function. F of negative 3 equals the opposite of f at 3. The points D and E are symmetric with respect to the origin, as can be seen graphically here. Px f of x belongs to the graph of function f as drawn. R negative x f of negative x belongs to the graph of function f as well. F of negative x equals negative f of x. The negative sign in the argument moves in the front of the function. F of negative x in the argument equals the opposite of the function at x. The points P and R are symmetric with respect to the origin. A function f is odd if and only if, whenever x, y is on the graph of f, then the point negative x, negative y is also on the graph. That leads us to the theorem, a function is odd if and only if its graph is symmetric with respect to the origin. Determine which of the functions below are odd. A is not an odd function. We check here to see if we can find symmetry with respect to the origin, looking at points D and E as reference, but we can see that E's y value is greater than D's y value in the positive direction. Thus, we can tell that this is not a symmetric function over the origin. B, however, is symmetric over the origin. D and E are perfectly symmetric with respect to f. C is not an odd function. There is no symmetry with respect to the origin, and we can see that the symmetry present here is actually with respect to the y-axis, so we can tell it's an even function. Determine whether the functions below are even, odd, or neither. A is even. A is even because it shows clear symmetry with respect to the y-axis. B is odd due to its symmetry with respect to the origin. C is neither because when assessing symmetry with the y-axis and the origin, it clearly has neither of those traits. And D is odd because it shows this nice symmetry with respect to f. When we use D and E as their reference points, we can see that that happens. Important. The domains of even and odd functions must be the set of real numbers or the open interval negative a, or the closed interval negative a, or any of the sets above from which a symmetric set is removed. Example, closed interval negative 3, 3 minus closed interval negative 1, 1, which results in closed interval negative 3, negative 1 open interval, united with open interval 1, 3 closed interval. Important. The domains of even and odd functions must have symmetry with respect to the origin. Another important. The domains of even and odd functions cannot be closed interval AB or open interval AB, because the graphs of even functions have symmetry with respect to the y-axis, and the graphs of odd functions have symmetry with respect to the origin. For example, the function f of x equals square root of x is neither odd nor even, because the domain of the function f is closed interval 0, open interval infinity. There is no symmetry in the graph of the function square root of x, as seen. Determine algebraically whether the function is even, odd, or neither. A. F of x equals x to the fourth minus 3x squared plus 5. The function f is a polynomial function of degree 4. Its domain is the set of real numbers. F of negative x equals negative x everything to the fourth minus 3 times negative x everything to the second plus 5, which equals x to the fourth minus 3x squared plus 5, which equals f of x. Thus, f is an even function. B. G of x equals 1 minus 2x squared divided by the quantity x cubed minus 4x. The function g is a rational function. Its domain is the set of real numbers minus the set made of negative 2, 0, 2. The domain has symmetry with respect to the origin. g of negative x equals 1 minus 2 times open parentheses negative x, close parentheses, everything squared, over the quantity negative x, everything to the third, minus 4 times negative x, which equals 1 minus 2x squared, everything over the quantity, negative x cubed plus 4x. Factor a negative 1 in the denominator, obtaining negative fraction 1 minus 2x squared, everything over x cubed minus 4x, which equals negative g of x. Therefore, g is an odd function. C. H of x equals the square root of x squared minus 4. The function h is a square root function. Its domain is open interval negative infinity, negative 2, close interval, united with, close interval 2, open interval infinity. The domain has symmetry with respect to the origin. H of negative x equals square root of negative x, everything squared, minus 4, which equals square root of the quantity x squared minus 4, which equals h of x. Thus, h is an even function. Decide whether the statement is always, sometimes, or never true. A function whose domain is all real numbers is both even and odd. Analytical approach. Assume that there is a function that is both even and odd. Thus, f of negative x equals f of x, and f of negative x equals negative f of x for all x in the domain. Therefore, according to the transitive property of equations, we can conclude that f of x equals negative f of x for all x in the domain. Add f of x to both sides of the equation, equivalent to 2f of x equals 0, equivalent to f of x equals 0. Thus, the only function that is both odd and even is the zero constant function. In conclusion, the statement is sometimes true. True or false? The difference of two odd functions is an odd function. Let h equal f minus g, where f and g are odd functions. H of negative x equals f minus g of negative x. Apply the definition of difference of two functions, equals f of negative x minus g of negative x. F and g are odd functions, thus the negative signs in the arguments move in front of each function. Equal to negative f of x minus negative g of x. Factor negative 1 from both terms. Negative open bracket f of x minus g of x, close bracket. Apply the definition of difference of two functions, which is equal to negative f minus g of x, which equals negative h of x. Thus, according to the definition of odd functions, h is an odd function since h of negative x is equal to negative h of x. The statement is true. True or false? If f is an even function and g is an odd function, then f composed with g is an odd function. Let h equals f composed with g. F is an even function and g is an odd function. H of negative x equals f composed with g of negative x. Apply the definition of composition. Equals f open bracket g of negative x close bracket. G is an odd function. The negative sign in the argument moves in front of the function, which equals f of open bracket negative g of x close bracket. The function f is an even function, thus the negative sign is absorbed, obtaining f open bracket of g of x. Apply the definition of composition of functions, equals f composed with g of x. which equals h of x. We have proved the function h is an even function. Thus, the statement is false. Decide whether the statement is always, sometimes, or never true. If f is an even function, then the function f of x plus 3 is an even function. F is an even function, thus its graph has symmetry with respect to the y-axis. The graph of f of x plus 3 is a vertical shift of the function f. The graph of f of x plus 3 also has symmetry with respect to the y-axis. In conclusion, the function f of x plus 3 is an even function. In conclusion, our statement is always true. Decide whether the statement is always, sometimes, or never true. If f is an even function, then the function f of x minus 3 is also an even function. The function f is even, thus the graph of the function f has symmetry with respect to the y-axis, as seen right here. The graph of f of x minus 3 is a horizontal shift of the graph of f. The graph no longer has symmetry with respect to the y-axis, unless f is a constant function, as seen in the function y equals 1. In conclusion, the statement is sometimes true. Extensions. Operations and even functions. The addition, subtraction, multiplication, division, and composition of two even functions are even functions. Transformations and even functions. The horizontal and vertical stretch or compress of an even function are even functions. The vertical shift of an even function is also an even function. The horizontal shift of an even function is neither odd nor even. More extensions. Operations and odd functions. The addition, subtraction, and composition of two odd functions are odd functions. The multiplication and division of two odd functions are even functions. Transformations and odd functions. The horizontal and vertical stretch or compress of an odd function are odd functions. The vertical and horizontal shift of an odd function are neither odd nor even functions. Use the table to determine if the function is even, odd, or neither. The points -5, -3, and 5, 3 are symmetric with respect to the origin, as seen in this chart B and G. The points -4, -1, and 4, 1 are symmetric with respect to the origin. Points C and F, as shown. The points -3, 2, and 3, -2 are symmetric with respect to the origin. Points D and E on the chart. The points -1, 0, and 1, 0 are symmetric with respect to the origin. Points A and H on the graph. The graph has symmetry with respect to the origin. Thus, according to the values in the table, the function f is an odd function. B. The points -5, -3, and 5, -3 have symmetry with respect to the y-axis. B and G. The points -4, 1, and 4, 1 have symmetry with respect to the y-axis. Points C and F. The points -3, 2, and 3, 2 have symmetry with respect to the y-axis. Points D and E. All the points on the graph have symmetry with respect to the y-axis. Thus, according to the values in the table, we can conclude f is an even function. Given that the function is even, fill in the table. A function f is even if and only if, whenever xy is on the graph of f, then the point negative xy is also on the graph. If the point -5, -3 belongs to the graph, then the point 5, -3 belongs to the graph too. If the point 4, 5 belongs to the graph, then the point -4, 5 belongs to the graph too. If the point -6, 2 belongs to the graph, then the point 6, 2 belongs to the graph too. Given that the function is odd, fill in the table. A function f is odd if and only if, whenever xy is on the graph of f, then the point -x, -y is also on the graph. If the point -5, -3 belongs to the graph, then the point 5, 3 belongs to the graph. If the point 4, 5 belongs to the graph, then the point -4, -5 belongs to the graph too. If the point -6, 2 belongs to the graph, then the point 6, -2 belongs to the graph too. And thus we filled in our table. Find the value of the constant a, given that f is an even function such as f of x equals ax squared plus open parentheses a minus 2 close parentheses x, positive 3a, -5. Graphical approach. The function f is even, thus its graph has symmetry with respect to the y-axis. The function f is a quadratic function. Its graph, a parabola, has the axis of symmetry x equals -b over 2a. The axis of symmetry is the y-axis if and only if b equals 0. The vertex is on the y-axis then. Thus, the coefficient of x, a minus 2, must be 0. A minus 2 equals 0 is equivalent to a equals 2. Analytical approach. The function f is even, thus f of -x equals f of x for all x belongs to the domain. Thus, a times -x everything squared plus the quantity a minus 2 times -x, positive 3a -5, equals ax squared, positive the quantity a minus 2x, plus 3a -5. Equivalent to ax squared minus the quantity a minus 2 times x, positive 3a -5, equals ax squared plus the quantity a minus 2x plus 3a minus 5. Cancel like terms. We cancel our reds, our purples, and our yellows. Add positive a minus 2 times x on both sides of the equation. Equivalent to 2 times the quantity a minus 2 times x equals 0 for all x in the domain. Equivalent to a equals 2. Given that x plus 3 is a linear factor of the even polynomial function f, which of the following must be true? If x plus 3 is a linear factor of f, -3 is a 0 of the function. Consequently, the point -3, 0 belongs to the graph of the function. But f is an even function. Thus the point 3, 0 belongs to the graph too. Therefore, 3 is a 0 of the function. As a result, x minus 3 is a factor of f. X plus 3 is a factor of f, and x minus 3 is a factor of f. Thus, x minus 3 times x plus 3, which equals x squared minus 9, is a factor of f. In conclusion, statement 2 is a true statement. There is not enough information to conclude either that the polynomial has degree 4 or that -3 has a multiplicity of -3. f of x equals x squared minus 9 is a polynomial function that satisfies the conditions of the problem. It has a degree of 2, and it has 3 and negative 3 as zeros. Both zeros have a multiplicity of 1. In conclusion, the only statement that must be true is statement 2. The correct answer is B. Given that the odd function f has a relative minimum equal to negative 5 at x equals 3, which of the following must be true? F has a relative minimum equal to negative 5 at x equals negative 3. F has a relative minimum equal to 5 at x equals 3. Or f has a relative maximum equal to 5 at x equals negative 3. F has a relative minimum equal to negative 5 at x equals 3. As a result, the point 3, negative 5 belongs to the graph of the function. Also, f is an odd function. Consequently, the graph of f has symmetry with respect to the origin. As a result, the point negative 3, 5 belongs to the graph 2, and it is a relative maximum. Statement 3 is a true statement. The correct answer is C. The end.